This lesson deals with supplemental problem 11.2. You can find this problem in the ECE202 ebook in the Chapter 11 Supplemental Problem starting on page 3. In our last video, we looked at the integrator of supplemental problem 10.6 and showed that it was unstable for a DC input. Could you redesign that integrator so that it is stable for a DC input? And then analyze the circuit using the techniques in supplemental problem 10.6. In supplemental problem 11.1, we did show mathematically that the integrator was unstable for a DC input. Let's take a look at the circuit and see if we can figure out why this is true. So here's our integrator. Now for DC, in steady state, this capacitor is an open circuit. So we break the feedback path between the output and the input. Now what does that imply? Well, the output voltage is equal to mu times V sub x, but now there's no feedback to tell V sub x to shrink. So as mu approaches infinity, our product then approaches infinity. For any DC input, the circuit's going to be unstable. Look at this another way. The circuit is a negative integrator. If you put a constant input, you're going to integrate that, and it's going to produce a ramp. So it's always going to be unstable. It's going to be approaching a very large negative number for a positive input voltage. All we can do is try and fix this case and see if the circuit can still work as an integrator for other than DC inputs. As we showed on the last page with our DC model, the circuit has a very large gain because the op-amp has a very large gain. So we need to fix this for DC, and one way we could do that is to make the gain finite. For DC, the cap is an open circuit. And it looks like an inverting amplifier, but we have no feedback. So let's put a resistor here. What that's going to do then is give me, for DC, when this is an open circuit, a gain of minus R2 over R1. I still want to use this as an integrator, so let's even figure out what frequency range this might work in, because eventually the capacitor's impedance will be smaller than the resistor R2, and it will dominate the parallel combination. Let's analyze the circuit and see if we can figure out the frequency range for this. With zero initial conditions, all we have for the capacitor is an impedance of 1 over SC2. So the gain is going to be equal to Z2 divided by Z1 with a minus sign. Z1 is just a resistor R1, so minus 1 over R1, and then Z2 is a parallel combination of R2 and C2, so we could add their admittances and then take the reciprocal. The admittance of the capacitor is SC2, the admittance of the resistor is 1 over R2. We multiply numerator and denominator by 1 over C2, we then get a minus 1 over R1 C2 divided by S plus 1 over R2 C2. The inverse Laplace transform of this is some constant K1 times e to the minus t over R2 C2. It would depend on the value of what we hook up for V sub s as we multiply that out and do our partial fraction expansion. But this term does decay as t approaches infinity, and our circuit then would be stable for DC. Now to be an integrator, we need to have the term 1 over s for our transfer function times some scalar. We have that expression right over here if this term here were negligible. So when the magnitude of s is greater than 1 over R2 C2, you could approximate this as a minus 1 over R1 C2 divided by s. And that would be the condition of the frequency range then for this to be an integrator. In other words, this is in magnitude just equal to omega. That would need to be much, much greater than 1 over R2 C2. In supplemental problem 10.6, we had that R1 was 1K, C2 was 0.1 microfarad, and V sub s was a 2-volt sine wave at 1 kilohertz. Now for our modified circuit still to be an integrator, we have to have that omega is much, much greater than 1 over R2 C2. So we could then pick R2 so that's true. R2 would need to be much, much greater than 1 over 2 pi f C2, and that's going to be 2 pi times 1K and 0.1 microfarad. That turns out to be 1.59 k ohms. So let's pick R2 much greater than that, say 100K. So our transfer function then is V out is equal to minus 1 over R1 C2 divided by S plus 1 over R2 C2 times our input Vs. So we get a 1K resistor, a 0.1 microfarad, 100K for R2, and a 0.1 microfarad for C2. And then our input was a 2-volt sine wave. So we have 2 times beta over S squared plus beta squared, where beta is 2 pi times F. The reciprocal of this is 10K. The reciprocal of this is 100. This is equal to 6.283K. And so we've got our expression now for V out. Now multiplying these constants, I get 125.66 times 10 to the 6th. I have S plus 100 times the quantity S squared plus 39.48 times 10 to the 6th. Let's find the roots of this, and S squared is going to be equal to a minus 39.48 times 10 to the 6th. Take the square root of that, and we're going to take the square root of a negative number, so we'll have a plus and minus j. And then the square root of this, of course, is just what we started with, 6.283k. We can write this then as k1 over s plus 100 plus k2 over s minus j 6.283k, and then the conjugate of k2 divided by s plus j 6.283k. Really, this is the conjugate of this. Let's solve for k1 and k2. We'll take our expression and multiply it by s plus 100 and let s equal minus 100. Cancellation. And we just get this quantity divided by minus 100 squared plus 39.48 times 10 to the 6th. That turned out to be a minus 3.175. For k2, we'll take the same expression and multiply it by this root. So s minus j 6.283k, and then evaluate it s equal to plus j 6.283k. get our term cancellations. We get this quantity divided by J, 6.283K plus 100. And then we have two of these, so 2 times the quantity J, 6.283K. Put this into polar form, 6.283K, and the angle is very close to 90 degrees since this is much shorter than this. Of course, this is just going to be equal to the magnitude at an angle of 90. Okay, so take the magnitude of the numerator divided by the magnitude of the denominator, get 1.5915. The angle of the numerator is equal to 180 degrees, and I'm going to subtract the denominator, which is also very close to 180 degrees, and so I get very close to that, just equal to 1 degree. So a very small error. So I can put together my inverse Laplace transform. It's going to be equal to minus 3.175 times e to the minus 100t from this term right here, and then double the magnitude of quantity, the cosine of the frequency 1k, and then the angle is the 1 degree that's here, and all times u of t. This is a time constant, so I'll take the reciprocal of that, and I get 10 milliseconds. And so here's my final expression. It's a minus 3.175 times e to the minus t over 10 milliseconds, plus 3.183 times the cosine of 2 pi 1 kt plus 1 degree times u of t. Now this is going to die out as time goes on. If this is a perfect integrator, this would be equal to 0 degrees. And so it's pretty close. So it's roughly minus 1 over r1c2 times the integral of v of s. Let's check out our results on PSpice. V out has a natural response that will die out in 5 time constants, in other words 50 milliseconds. So I'm going to take that input file and change it to 50 milliseconds for my final step of time. Now I'm going to do a lot of cycles, so let's put 2,000 data points on the screen. So I'm going to divide 50 milliseconds by 2,000 to get 25 microseconds. Start plotting at t equals 0 and make the ceiling step the same as the print step. And you can see just that. We're getting a response that eventually is reaching steady state. Let's zoom in on these last 2 cycles and see what's happening. So here's my output, and it's going between 3.151 and minus 3.198. Now we're predicting that this peak would be equal to 3.183, and we're a little bit off because there is a phase response in there of 1 degree. Let's take a look at the input. The input is here. It's a sine wave, node voltage 1. And you can see that this is the integral of this, whereas the integral of sine is minus cosine. But we also have a minus sign from the inverting amplifier. So we just get the cosine function here. So indeed we get the same results in steady state. And this is supplemental problem 11.2.